जी सर।
अच्छा, enthalpy of combustion हो गया था. We're going to start with standard enthalpy change of neutralization, ठीक है, which is the energy change associated with the neutralization reaction. So it's the standard. So this is the standard enthalpy change. Change of neutralization. So basically it's the energy. अच्छा पहले बताओ, is this exothermic, endothermic? What is it?
एक्सोथर्म।
ठीक है, neutralization is always exothermic. And the definition, remember definition, they're going to ask you for the definition. So it's the energy that is released. So it's the energy that's going to be released when 1 mole of water is produced. Okay, whenever you have a neutralization reaction, so 1 mole of water gets produced. Is produced when what happens? When an acid and an alkali react. Yeah, acid and a base react. And it's going to be measured under standard conditions. Achha, so one thing is it's supposed to be 1 mole of water that's going to be produced always. It's, remember, bases and acids, there are many acids and bases. We're talking about a specific reaction in which water is going to be produced. So usually acid and base, what do? They produce salt plus water. So you have acid plus base, and they're going to react together to form salt plus H2O. But it's got to be 1 mole of this, has to be 1 mole at all cost. So in any neutralization reaction, if you have 1 mole of water getting produced, that's enthalpy change. Its enthalpy change, its energy change would be called delta HN. So for example, you've got acid HCl and you've got NaOH. And it's going to produce what? NaCl and H2O. So 1 mole of water getting produced, that, so the enthalpy change would be called enthalpy change of neutralization. You'll call it delta HN. That's another example. If I have H2SO4 and that H2SO4, let's say, reacts with KOH, it will produce what? It will produce it's going to produce K2SO4, and it's going to produce water molecules. Okay. So can I, and if I balance this out, okay, this is the balanced equation. Can I call the energy change of this reaction the enthalpy change of neutralization? ये होगा कि नहीं होगा? Is this standard? Is the energy change associated with this reaction the enthalpy change of neutralization? अच्छा, जो लेट है उनको मैं फिर से explain कर देता हूँ कि enthalpy change of neutralization is simply the energy that is released when a mole of water is produced. When what happens? An acid and a base, they react. So whenever an acid base react, 1 mole of water exactly is produced. The energy change for that reaction is going to be called the delta HN, or enthalpy change of neutralization. Okay. अच्छा, इसका क्या है, Rafe? What is this? Is this neutralization or not?
No, sir.
ठीक है, because you've got 2 moles of water in this case. Okay, so over here you've got 2 moles of water getting produced. So you can still call it the enthalpy change of neutralization, but it's twice the amount. It's double the enthalpy change. Enthalpy change of neutralization is for 1 mole. So if you're producing 2 moles of water in an acid-base reaction, the energy produced is double the amount. Okay. So is that clear? Ahmed, is this clear? Abdullah, is this clear? Is Ahmed clear? Okay, what is
Yes,
delta?
sir.
So this is delta Hn, right? Achha, one thing, first thing, can anyone answer me? Why is it always exothermic? Achha, one thing is that it's always exothermic. The other thing is, no matter what the acid or base is, the enthalpy change of neutralization always has the same value. So both of these reactions, they kind of have the same value. So for strong acids, so any acid, you use any acid and any strong base, delta Hn is always equal to around minus 57 kilojoules per mole. So it doesn't matter which acid you're going to use. The energy that's going to be released would be always exactly the same. Okay, if I put another reaction in, and let's say I'm using HCl, I use another acid. Let's say I use HNO3, and over here I use another base. Let's say KOH. So the enthalpy change, although it's a different reaction, but a salt and water is produced. Salt case, it's going to be KNO3, and you'll have water getting produced as well. But the enthalpy change will, for both reactions, would be exactly the same. What reason also? Why is it always the same? Even when you use a different. The idea, Rafe, Ahmed.
Spectator ion.
Okay, because the rest are all spectator ions. Because what happens is that the role of the acid is that it produces H+1 ions. So it doesn't matter whether it's HCl or HNO3 or H2SO4. The role of the acid is that it produces H+1 ions. The role of the base is that it produces OH ions. And the reaction in all cases, what happens is the H+1 and OH ions, they're going to combine and they're going to form water, 1 mole of water. So every time the reaction is always the same. So it doesn't really matter which acid you're going to use. The rest of the ions are spectator ions. They're not doing anything. But the Cl has no role to play in this. NO3, SO4, they have nothing to do in the reaction. The only thing is that it produces H+1, this produces OH ions, and the H+1 and OH ions, they combine to form H2O. So the rest of the ions are, so whether you use NaOH or you use KOH, it's the same thing. Is this clear?
Yes, miss.
The rest of the ions are spectator ions, and so it doesn't matter NaOH, KOH, as long as it produces OH ions. And the overall ionic equation is this one. The one that's in front of you, that's the ionic equation. And every time you have the same ionic equation. And the enthalpy change delta Hn is usually close to minus 50. Let's go minus 50. So that's usually minus 57 or something close to minus 57 kilojoules per mole. As a secondly, you've got weak acids as well, weak acids and weak bases. So remember this, that for weak acids, the value is slightly less exothermic. So for weak acids and bases, delta Hn is slightly less exothermic. So the first question is, why is it slightly less exothermic? Or iski jo range hogi na, that would be around -52 to, let's say, anything less exothermic, -52 kilojoules to maybe -55 kilojoules per mole. So what's wrong with weak acids? Why is it less exothermic? Like when you do the same reaction with a weak acid, for example, and which ones are weak acids and which ones are weak bases? Okay, most of your organic acids, like carboxylic acids, you've got other acids as well, but that's one main example. So carboxylic acid, that's weak. That's a basis where you've got nitrogen bases. So nitrogen bases, like ammonia or amines. Like examples like ammonia is NH3 and amine is NH2, etc. Right? Carboxylic acid is like this, it's RC. So organic acids are usually weak acids. They don't ionize a lot. And organic bases are nitrogen bases. Can anyone tell me why strong acids, strong bases, the enthalpy change is -57, but if you have a weak acid, weak base, so why is it less exothermic? क्या होगी रीजन? इसमें बोर्ड लिंक में शेयर करो यहाँ पे. Ahmed, Rafi, what could be the reason for this?
Weak acids to ionize partially.
Okay, so energy is needed to ionize them. If you have a strong acid will produce a lot of H+ ions itself. You don't have to do anything. But a weak acid will not produce H+ ions. They ionize partially. So weak acids and weak bases. So the reason for it being less exothermic is that energy is needed to ionize them. Weak acids and bases ionize weakly. So energy is needed, which makes it slightly endothermic or less exothermic. So energy is needed to ionize them so that they can produce H+1 ions. For example, if I do a reaction of ethanoic acid with NaOH. Now the ionic equation is the same. The acid will produce H+1, the base will produce OH ions. The H+1 from the acid will combine with the OH ions and they're going to produce water. And what's left is your salt. That's the thing that's going to be. So that's the thing that's going to be left, which is CH3. And Na+1. So that is what is left. So it's the same exact reaction. The only problem is that ethanoic acid will not produce H+1. You would have to ionize it, and you would have to give it energy so that H+1 ions could be produced. So yeah, so I'll just sum this up. Otherwise, we're done with this. You need to remember the definition. What is the definition of enthalpy change of neutralization? It's 1 mole of water being produced, acid base reacting. So there's going to be a certain amount of energy that would be released. And any acid base reaction, 1 mole of water getting produced, that's going to be called the enthalpy change of neutralization. It always has the same value for strong acids and strong bases, which is around -57. Why is it always having the same value? Because it's always the same reaction. The other ions, whether it's HCl, HNO3, they're all spectral ions. और फिर ये था कि we've got weak acids and weak bases. Their enthalpy change of neutralization is slightly less exothermic. Why? Because weak acids, they don't tend to ionize. They don't produce H+ ions that readily. So if I want ethanoic acid to produce H+ ions and give it to OH ions, it's not going to do that readily, at least not readily. It needs energy so that the H+1 can leave and the OH can accept it. So some energy is needed for the reaction to happen, which is why it's not as exothermic as the previous reaction. So is that all clear?
Yes.
In the same thing, we did E definition. We'll just do a couple of questions. Okay, they would be simple, not that difficult. What we're going to do, that's going to be very challenging. Okay, that's one specific topic that is difficult. I mean, sticking to chemical energetics, we just did definitions at the moment. I said delta HN ke thoda se questions, maybe some MCQs. So that's all about enthalpy of formation, and I say usi ka question kar lete ki can anyone tell me what is X over here? Like, how can you define what X is? I mean, that's not delta HN, by the way. It's water being produced from its elements. And everything, so H2 and O2, they're producing H2O. So what would you call this?
Enthalpy change of formation.
You can call it delta HF, right? And but it's 2 moles of water getting produced. So it's delta HF multiplied by 2, right?
It's 2.
So D is right. You can also call it, X enthalpy of combustion as well. Hydrogen burning with O2 to produce H2O, right? You can call it delta HC as well. Enthalpy of combustion of hydrogen, right? But that
sir, we are not sure if the oxygen is going to be in excess or not.
Yeah.
Sir, how will we know if the oxygen is in excess or not?
Because you're getting complete combustion. What happens when hydrogen burns? You get H2O, right?
Yes.
So incomplete to nahi na, it is complete combustion. Okay? So it is enthalpy change of combustion. वो products देख के पता लग जाता है ना whether it's complete or incomplete. You just look at the products. Now in this case, so this is enthalpy of combustion of hydrogen, but into 2 because you're burning 2 moles of hydrogen. So ये भी सही था. The only problem was that it's not 4, it's 2. Is that clear?
Yes, sir.
So then we've got which energy change corresponds to the enthalpy change. Atomization is no longer here. This is about neutralization. What is happening here? Okay, there's this reaction, and they've told us that the enthalpy change for this reaction is minus 114. Is this delta HN or not? Is energy changes? Is this enthalpy change of neutralization or not?
No, sir.
Okay. It's 2 times the standard enthalpy change of neutralization, right? Because you're producing 2 water molecules. So minus 57 ही बन जाता है. You're going to get minus 57 for this. So now what they're asking for is that they're asking for this other enthalpy change for this reaction. What would be the enthalpy change for this reaction? You got a base reacting with an acid produces salt and water. So is it going to be the same value or is it going to be a different value?
It's going to be the same.
It's going to be the same value. Remember, I just told you that enthalpy, because 2 moles of water were being produced in the first reaction, 2 moles of water are being produced in the second reaction. It's a strong acid, strong base, strong acid, strong base. So delta HN is always around equal to minus 57. So both of them would have the same value. This is 2 times delta HN. So it's going to be minus 114. Okay. Similarly, we've got, clear? Is this clear? Ahmed, Abdullah, Rafi, is this clear?
Yes, sir.
I said the next one is you've got, they're just asking for the signs. Atomization is not in your course now. And solution is not in your course as well. So if you're just left with formation. Formation, remember, can be plus and minus both. So again, this is atomization, not in course anymore. As this one, delta HN. So minus 57, that's strong base, strong acid, right? So the first reaction is a strong base, strong acid reaction. Now you've got minus 54. Is it a strong, so is P going to be a strong acid or a weak acid?
A weak acid.
It's going to be a weak acid. I just told you that if you have a weak acid or a weak base, the enthalpy change would be less exothermic. It's going to be less than minus 57. So the answer would be, it's going to be ethanoic acid. P would be ethanoic acid, not sulfuric acid. As similarly, this one, this is also, is this going to be a weak base or a strong base?
Weak base.
You get minus 52, that's going to be a weak base, right? So ammonia is the weak base. Last one, minus 57, strong or weak?
Strong.
Okay, so that's potassium hydroxide. You can remember weak mein kaun se aate hain? Weak mein you've got organic, carbon-based acids, and you're going to get nitrogen bases, like ammonia. So you've got this reaction. What would you call this? Can you describe the enthalpy change as formation or combustion or both? I mean, is this formation or is this combustion or is it both?
Both.
I think it's
It is both. Okay, the enthalpy change can be described as the enthalpy of formation of water, and you can also label this as enthalpy of combustion of hydrogen as well. Because if you burn hydrogen, you get the same reaction, exactly same reaction. So you can describe it as both. Negative hoga, positive. What would be the value?
Negative.
Okay. And the reason it's negative is that, as I remember, both of them are the same thing. I mean, formation and combustion, they both represent the same reaction. Formation can be plus and minus. It's hard to figure out what formation is, but combustion is always negative. So the answer to this one is it's going to be negative because it can't be positive. I mean, both of them are representing the exact same reaction. So if you call it combustion, combustion always is exothermic. So which is why it's obviously negative. But if you describe it as formation, it can't be endothermic because you're calling it combustion as well. So this one last, which one is equal to the standard enthalpy change of formation of propane? Propane is CCH8. Formation of propane, the enthalpy change. कौन सा सही?
let's see.
C.
Element, carbon is a solid, hydrogen is a gas, H2 at room conditions. So 1 mole of propane is formed from its constituent element. So it's going to be C. So let's, this is just basics, okay? But remember the small details. Now, what we're going to do is, now this one is difficult. The next subtopic, the small topic that we'll do, this next part is difficult. We'll probably I'll just give you an intro of this. I said there are 2 ways of actually doing this. There's an easy way and there's a difficult way. There are formulas which are easy. But we're going to do the difficult part first. So the idea is, as a first thing about definitions, remember they won't give you the equations. All data will be represented in the form of delta HF, delta HC, delta HN, and so on. So now this next subtopic is known as Hess Law. Or Hess's law. So what is the Hess law? The Hess law simply states that first thing, the definition, it is that the energy change or the enthalpy change of a reaction is the same no matter what path is taken. So basically, it means that if you would do a reaction, no matter how you do it, as long as you get the products, the enthalpy change would be exactly the same. As an example, I've got this reaction. I've got carbon burning with O2. And when it burns with O2, it produces what? It produces CO2. Okay, so you got carbon burning with O2 and they end up producing CO2. And carbon is a solid, oxygen is a gas. Okay, make sure you be careful with the states whenever you do anything. And this reaction has a certain enthalpy change. It's going to be exothermic. Let's call it delta H1. You can give it different names. You can call it the enthalpy of formation of carbon dioxide. You can call it the enthalpy of combustion of carbon as well. I'm just going to call it delta H1. Delta H1. So I want to burn carbon to produce carbon dioxide. Now I can follow another path. Basically, what I want to do is my starting point is this. These are my reactants. And I need to make my products. I need to get to the other side, right? So one of the method is I can directly do this. Or what I can do is I can first burn carbon in a limited supply of oxygen. And that produces carbon monoxide. And there's half oxygen left. So I'm not going to completely react the carbon. I'm going to just react it in a limited supply of oxygen to produce carbon monoxide. And then the same carbon monoxide, I'm going to burn it again in oxygen and produce carbon dioxide, right? So that is another route that I can take. Okay, so is this part clear? You can have multiple routes for a reaction. Like I wanted to make carbon dioxide, I could do it this way as well. Is that clear?
Exactly.
Yes, sir.
So now the thing is, this particular path over here will have a certain enthalpy change, delta H2. Like you burn carbon in a limited supply of oxygen. You just use half of the oxygen, not all of it. And you end up producing carbon monoxide. So a certain amount of energy would be released or absorbed. Then burning the carbon monoxide again, a certain amount of energy would be released, mostly released because it's combustion. So now the other part is you've got this cycle. What did Hess Law state? Hess Law states that this path over here and this direct path and this indirect path over here, they have the same enthalpy change. Because at the end of the day, you're making carbon dioxide, right? At the end of the day, so at the very end of the day, so at the end of the day, you're making carbon dioxide. And since you're making carbon dioxide, you would be, because your net bonds broken form, they would be exactly the same. So path 1 and path 2 would be having exactly the same energy change. This is path 1. and this over here is my path number 2. So the energy changes would be exactly the same. So I can come up with a relationship. Path 1 equals path number 2. Path 1 has this energy change. It's delta H1. So part 2 is delta H2 plus delta H3. What I've got over here is that I've got a relationship now between the different enthalpy changes, delta H1, delta H2, delta H3. That means all 3 enthalpy changes of 3 separate reactions are basically interlinked with each other. They have a relationship with each other. Delta H1 is equal to delta H2 plus delta H3. Now, if any one of them is missing, you can find it out. Like if you know delta H1 and delta H2, you can find delta H3 by using delta H1 and delta H2. If you have delta H3 and delta H2, you can find out delta H1. Okay, so is this clear? This is what Hess law is. That the enthalpy change of reaction is the same no matter what path is taken. So you can take a different route as long as you reach the same point, as long as you produce exactly the same thing. Okay, so is this clear?
Sir, I have a small question.
Yes.
So, and delta H1 is equal to delta H2 and 3. So that means that delta H2 and 3 will be having a lesser value than delta H1. Is that right?
Okay, that obviously makes sense. Okay. But basically the idea is that you had, if I break this up, it's basically 3 separate reactions, right? What Hess law did was, you've got 3 separate reactions, but let's go. Now this is known as the Hess cycle. Okay, this what you have over here is what is known as the Hess cycle. That you can create different paths for a particular reaction, and this is known as the Hess cycle, and you've got
The reactions.
ये क्या मैं बात कर रहा था? Yes, I got it. So basically, what the Hess law or the Hess cycle did was that you had 3 completely separate reactions, which had nothing to do with each other, like carbon burning in oxygen to produce carbon dioxide, right? Then you had carbon monoxide burning in oxygen, and it was producing carbon dioxide as well, and it was burning with half oxygen. And then you had carbon burning in half oxygen to produce carbon monoxide, right? And the enthalpy changes were, for the first one, it was delta H1, I think, and the second one was the carbon dioxide, that's delta H3. And then you had delta H2. So what this cycle did was that apparently 3 separate reactions, the cycle helped us connect them together. Okay, so there were 3 completely random reactions. All of them were separate, but the cycle helped us figure out that they have a relationship with each other. Okay, and this relationship is very important to figure out the unknown enthalpy changes. Like if one of the enthalpy changes of these reactions was missing, you can figure this out. Okay, clear? Is this clear?
Yes.
So in the end, I'm just going to redraw this, and also remember that. So let me just. Also remember that the paths that you select, there could be any 2 paths. It's not necessary that you select, as long as the starting and end point are the same. So what can also happen is that I can choose this as my path, one of the paths, right? So what's the other route? The other route is I go all the way from the other side. As long as my starting point and end point are the same. Okay, is this point clear?
Yes.
Sorry?
1 second. I'm just saying to apply Hess law. So यहाँ पे था ना, I chose one path. This is one path, and that's the alternate path, right? And what did I do? I equated the two paths together, that their energy changes were exactly the same. What I'm saying is, if you have the same cycle, you could choose any paths and make them equal, as long as they're equivalent paths. कि यहाँ से यहाँ जाना, that's path number 2, right? What's the other path? What's the other way to go around? You go all the way from the other side. So these two paths are equivalent. I'm going to get exactly the same relationship. There's not going to be any difference. Okay, I'm going to get path 1. Let's say making it equal to path 2. So now look at path 1 now. I have to go in this direction. If I want to go in the opposite direction, the enthalpy change sign will reverse. So instead of delta H2, I'll have minus delta H2. Okay, look at path 1. Okay, I have to go in the opposite direction. So if I want to go in the opposite direction, this is going to be minus delta H2. Iski direction, that's minus. So this is all right. So this is going to be plus delta H1. And what is path number 2? Path number 2 is you can go directly from here to here. That's delta H3. So the point I'm trying to make is, it doesn't matter which paths you select, because it's a cycle, right? So you can have any starting point, you can have any end point, as long as the two paths, they end at the same point and they start at the same point. Okay, so the relationship is exactly the same. This relationship is just rewritten in a different way, but this is exactly the same relationship. Okay, is this point clear?
Sir, like, why will we be like obtaining the elements form and then go back to the carbon dioxide?
Yeah, I'm not saying, I'm just saying that once you have a cycle, right? Okay,
Yes, sir, like, but by which reaction is that possible?
Okay, going back?
Yes, sir.
If you know okay, carbon and oxygen, they react to form carbon monoxide, right?
Yes, sir.
By default, you know the reverse reaction as well. Whether it's going to happen or not, that's a different story. I'm just saying, okay, agar forward jaane mein na, the reaction has an enthalpy change of, let's say, 100 kilojoules, right? Then going in the opposite direction, the reaction will have the same enthalpy change, but will have the opposite sign. If, for example, agar aap forward ja rahe na, you're breaking some bonds and you're forming some bonds, right? And like over here, you're going from carbon to oxygen and you form carbon monoxide, right? So you're going to break the oxygen bonds and the oxygen will then combine to form carbon monoxide, right? If you want to go back, you're going to do everything in the opposite direction now. You're going to break the carbon monoxide bonds and you're going to form the oxygen bonds. So the point I'm trying to make is that even pata hona chahiye ek cheez hai ki if I have a reaction H2 plus Cl2 and 2HCl, if I want to go in the forward direction, the enthalpy change will have, let's say, this value plus 100. But if I want to go in the backward direction, the enthalpy change will still have the same value, but it will be minus 100. Because the bonds that you were breaking, you're now forming those bonds, and the bonds you're forming, you're now breaking them. Okay? So if you're going in the reverse direction, the enthalpy change sign will change. Okay? But your point is, okay, why are we going in this? We're not going in this. We're just constructing a Hess cycle. Okay? We're not actually performing this reaction. We just knew the enthalpy changes. Somebody told us that these are the enthalpy changes, and the third one was missing. Using these reactions, I was able to make a Hess cycle. Now I can go anywhere in the Hess cycle. Okay? I just want to complete this calculation, right? So it doesn't really matter. You can, now once you have a Hess cycle, you can go in this direction, you can go from the other direction. Or what you can do is you can choose any paths. Okay? It's up to you. It's every time it's going to be the same thing.
Okay, sir.
Okay, clear?
Yes, sir.
The reaction, the most likely would have happened in this way. I mean, most likely it would not have happened in the backward direction. But I'm just saying that if this is delta H1, you go backwards in the opposite direction, that's minus delta H1 then. Whether you are actually doing it or not, that's a different story. Okay. So, sir, okay, let's continue tomorrow then. We'll the basic idea, is that clear? The basic idea.
Yes, sir.
एक बस छोटा सा चीज है कि which is we're running out of time. अच्छा, what if I had this path? Okay. So what if I had this path, which is I start here and I pura circle karke I come back to the same point. So what would be this path equal to? What would be the total energy of this path? I just have one path, let's say. I start here and then I do everything and then I end at the same point. What would be the enthalpy change for this value, for this path? Like path 1 over here would be equal to, it's going to be equal to 0. Why? Because you overall did not do anything. You started with carbon and oxygen, you did everything, then you came back and you formed carbon and oxygen back again. So kya kiya aapne? You didn't do anything actually. In total, you didn't do anything. So the enthalpy change of this entire path would be equal to 0. Is that clear?
Yes, sir.
Yes, sir, because of delta H3 and delta H2 being minus, right?
Because of?
The subtraction of the difference.
Lekin the point is that the reason this entire path is equal to 0 is that you started at carbon and oxygen, right? Beach mein you did a lot of things, but at the end of the day, you still have carbon and oxygen, right? So overall, what did you do? Overall, you didn't do anything. Okay, so if you didn't do anything, the enthalpy change would be 0. So that means delta H1 minus delta H3 and I think minus delta H2. That's equal to, all of that is going to be equal to, it's going to be equal to 0, right? So all of that is going to be equal to 0 and yep, that's it. But remember, it's the same Hess cycle. So all of these expressions are exactly the same. Delta H1 minus delta H3 minus delta H2 is equal to 0. This one, it's the same expression. There's no difference whatsoever. Or jo pehla wala na, that's still the same expression. It's just rearranged. They're all just rearranged. So ye paths, ठीक है, तो बस ये paths का ना practice कर लेंगे थोड़ा सा और. अभी तो खैर हमने बहुत करना है. We have to like do a lot of questions on this. So let's continue tomorrow then. ठीक है. So okay everyone.
Love is it.
Love is.